So this discussion I want to talk about how we deal with transistor channel modeling, but particularly how we look at it for dendritic cables. And part of this is going to be how do we look at dendritic cables and look at how do I take what is a piece of dendritic structure, going through transistor models, and then by so doing I linearize these models. And this feels very similar to sort of classical neuroscience model for cable theory, which you might find from like Rall's model of a typical structure, typical piece of cable. Now, let's start with just starting off with the fact that a piece of dendrite, well, dendrite cable is going to have sort of inside, sort of outside and then inside and then outside, sort of some circular but diameter, but really it's going to be whatever kind of interesting shape it is. We'll have internal potentials, and say we're looking at in the middle of a cable, so V sub k, k plus 1, k minus 1. And I also may have, say, start off with say, 1 synapse per block. I could have many synapses, and we could look at multiple things, but start from this in terms of a model. And so I'm going to be dealing with synapses plus, and there'll be channels, channels to the outside. And we know that a channel actually is a voltage control barrier, and therefore fits very much what you see for a subthreshold transistor. All this is really quite useful. And so we might imagine 2 channels there and there. If I look at this model and try to build it, I might go, well, I've got my transistors for channels. That works well. I actually have transistors here for the synapses. And there's going to be some other gating mechanisms around the synapse, but we'll start off with a very simple transistor model, maybe going up to calcium potential in this case. Can be done in multiple ways, but just to start with. And then when I look at the element between these blocks from k minus 1 to k and k plus 1, we're typically talking about a diffusive process. And interestingly enough, at a continuous level, that feels like a single transistor. Because if you look at the transport in a transistor in subthreshold, you're dealing with diffusion of carriers from source to drain and from drain to source. And these transistors typically, if I'm using them for the modeling here, it's typically going to be in the ohmic regime. And so I can do things with this. Now, I often will take things where I'll have floating gate elements in here in practice because I can use charge to program the exact values I want. Because if you notice, a typical cable is not all the same size. There's a definite change in the diameter. And that matters in many, many different properties. And so as a result, the change in the charge, both in the channel size, which gives you an idea of the size of the channels or the number of channels in a particular sort of cross-section, as well as the diffusion across, gives you some interesting places there. Now, for those who are kind of curious, like, well, wait a minute, what do I mean in ohmic regime? Well, this is what the current would be for a MOSFET in the ohmic regime with the source and drain terminal. We're not worrying about any early effect or dibble effects in this case, and this would be its gate voltage. Do notice that I can then, kind of move the source voltage out, therefore have this drain, and everything looks just as I would expect. Interestingly enough, though, I would normally say saturation, which is where we often use a lot of devices, and in fact would be true for this device going down to EK, at least for some of the region. It may in fact actually be ohmic for part of it, but certainly for the synapses they'd be in saturation, is when the voltage between the drain and the source is 100 millivolts, 4 UT. And even in biological cases you see voltages that big. Often, say, between the calcium potential and membrane potential, or number of different things. You can get 100 millivolts quite believably. By the way, UT factor is the same sort of exponential you're going to see in the biological cases as you would see in silicon. So, in silicon transistors. So no surprise there. And then when you go a little bit further with it, what you realize is that, okay, well, so saturation, I get a very typical case where basically this second term just disappears. But if I'm in the ohmic case, well, that's actually when these two voltages are really close to each other. And the way you start to approach that is you say, well, imagine they're close. Well, let me Taylor expand both of these being near zero. And what I find is that the term that pops out is really sort of the drain minus source voltage over UT. And so it does actually look like a resistor. Now for very small voltages, you got to stay within about a UT to make that work. But it does give you the ability to say, oh yeah, there's a conductance there. And so when I start to ask, what do I look at in these horizontal terms, this is precisely what I would expect. By the way, for the synapses, those are most likely also going to be floating gate devices because that allows me to then have a weighting value as well as an input value. There are ways to deal with the presynaptic part of that computation, but I definitely get a very nice multiplicative kind of function here with whatever its effective structure is. But here's what's interesting, is that I can look at the structure here, and then at least if I linearize both this transistor and this transistor, this one just looks like a current source because it's such a high potential. Your typical resting potential is about 10 millivolts above EK. Well, this transistor definitely sits in a ohmic regime. In fact, often the voltages down to EK are somewhere getting ohmic, but somewhere sitting in between, and that actually is something actually very special. So it's sort of in that ohmic regime, but sort of starting to push out of it. And so you start to see all of these questions. But what's important here is to understand that there's a very clear tie across all of these aspects, particularly in terms of what you might see a dendritic model, what you would see for a transistor-based approach, channel modeling approach, and then also, you could linearize that, and that gets back to sort of linearized models, which are sort of the early attempts to try to model what you see in dendritic cable. And all of these properties tend to be very, very helpful in being able to translate back and forth between different types of models and different model properties.